We're going to look at simple harmonic motion, and this is assuming that there's no opposing forces such as friction. Let's go ahead and look at an example of this. We're looking at no damping forces, so I'm turning that off. We're going to have this in motion. I'm just going to increase the mass and decrease our spring constant a little bit so we can see the motion of this. So if we put this in motion by pulling this mass down or by pushing this mass up, we see that we would get a motion something like this. The spring would go up and down, it would oscillate, and we see that it would look like a trig function. Now, as we're watching this, let's see what it would look like to have the velocity here. And so we're going to graph the position and also graph the velocity. And as we see that spring in motion, we can see the two interacting, the velocity function. We've got kind of this gold colored position function, and then we've got this peach colored velocity function. And you can see sort of when the velocity is 0 and at its max and its min, and of course the velocity would be 0 when this position is all the way either at its minimum or its maximum. So it's either stretched down as far as it's going to go in this oscillation or compressed as far as it's going to go in this oscillation. So let's go ahead and go back to our problem, and now we have sort of a sense of, we have this spring and mass, and we have a rest position, and then we have it hanging and it is stretched 5 units beyond its rest position and release. So we take this thing and we stretch this down by 5. This causes the spring to want to restore to its equilibrium position, so it's going to bounce up. But it will bounce past the equilibrium position and it will compress the spring, and a compressed spring, then the force of the spring, it wants to push it back to the equilibrium position, so it pushes it back, but on the way it will then come back down, and so this will oscillate back and forth. And the position at any time t after it's released is 5 cosine t. So we'd like to determine its velocity and its acceleration, and we can do that with calculus that we have learned. So we have s prime, which is the derivative of position, and that is the velocity, and the derivative of 5 cosine would be, we know the derivative of cosine t would be negative sine t, so this is going to be negative 5, we got the constant, sine t. And let's actually go ahead and look at those two graphs, and we see here that we have our position graph, which is 5 cosine t, and then we have our velocity graph, which is negative 5 sine t, and we can sort of see some of that interaction when we have this stretched all the way to its position of 5. The velocity is 0. As we let it go and the position goes back right here where it's at its equilibrium, we can see that the velocity function is at its minimum, which would be, if we were looking at absolute value, it would be at a peak here. And then as the spring moves and gets to negative 5 right here for its position, we see the velocity there is 0 just before the velocity, which was negative, changes sign and goes to positive. And the sign on the velocity just simply tells us the direction that it's moving. Positive and negative velocity is of course being opposite directions. And now our velocity function is positive here, and it is at its fastest when we are here at the equilibrium position, and then as we get out to 5, the velocity will again be back to 0. Now let's go ahead and figure out the acceleration. Acceleration is the derivative of velocity, or the second derivative of position. So if we differentiate this velocity function, the derivative of sine t is cosine t. So we have this negative 5 constant times the cosine of t. So looking at acceleration, acceleration follows a cosine t, but it is the actual reflection of the position. Let's go ahead and look at this graph. We have all three of these on here now. We have the position, we have the velocity, and then we have acceleration, which is the reflection of position. So basically our acceleration has opposite signs of our position, and our acceleration is 0. Now that's not our velocity being 0, it's our acceleration being 0 when we are at equilibrium here. And we can see that is when we have a maximum velocity. If we're looking at the magnitude of the velocity, it's going to have a negative sign on it here, but it is at a peak right here. And that at that point, because the velocity will be turning here, we see its derivative, its rate of change right at that instant is 0. Its acceleration at that point is 0. Now we're going to look at one more thing. We're going to consider the jerk. And the jerk is the derivative of acceleration, which would be the second derivative of velocity, which would be the third derivative of position. Now we had the acceleration to be -5. If we remember, -5 cosine t was what we got for acceleration. So if we take the derivative of that, the derivative of cosine is negative sine. That'll be multiplied by our -5, and we will be 5 sine t. And so if we're looking at our jerk, let's go back and look at our graph here. For jerk, we got 5 sine t, and so we could put the graph of the jerk in here. This would be 0, and when this one was 0, this would be at its maximum. So it would come in right like this, and then it would be back down here at 0, and then back at a minimum right here, and then back to 0. So here would be our jerk. So what this is essentially telling us is you would feel the most jerk, which would be the rate of change of acceleration right here, as our acceleration changes from negative to positive. And then again, you would feel this as our acceleration changes here from positive to negative.